NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Good, very good. Well, thanks for coming out. As always, we greatly appreciate your attendance here. The Cold Atom Laboratory, or CAL, is a multi-user facility for the study of ultra-cold quantum gases. Scheduled to launch in August of 2017, CAL will then be installed by astronauts into the Destiny module of the International Space Station. Facilitated by the microgravity environment of the ISS, CAL will achieve temperatures 1 billion times colder than the vacuum of space, making the ISS the home to the coldest spot in the known universe. It will explore the nature of gravity and dark energy, giving scientists access to an unexplored quantum realm. Tonight, we have both the project manager and project scientist to tell us all about this amazing new facility. Ladies first. Dr. Anita Sengupta has been a member of the technical staff at JPL since 2001. She started out working on and testing and improving the ion propulsion systems for Deep Space One and Dawn missions. After that, she led the supersonic qualification of the MSL parachute that landed the Curiosity rover on Mars. Her next roles were the development of mission concepts for a Venus lander, a Mars sample return mission, and a Mars ascent vehicle. For the past 5 years, she has led the development of the Cold Atom Laboratory mission as the project manager. She earned her MS and PhD in aerospace engineering from USC, where she is also a research professor and teaches spacecraft design. In her spare time, she is a pilot with the Caltech Flying Club, a sport motorcyclist, public speaker, and world traveler. Dr. Robert Thompson is the project scientist for the Cold Atom Lab and the developer of its conceptual design. Raised in Savannah, Georgia, he received his BS from Georgia Tech and a PhD from the University of Texas at Austin. He worked 2 years as a postdoc at the National Institute of Technology with Bill Phillips, a 1997 Nobel laureate in physics. He has been in the Quantum Science and Technology group at JPL for nearly 20 years, spending much of that time developing technology for future space-based cold atom missions. With all his spare time, he teaches courses about the science of sustainability and the future of science and technology at the Art Center College of Design right here in Pasadena. Ladies and gentlemen, please help me welcome our guests tonight, Dr. Anita Sengupta and Dr. Robert Thompson.
Well, thanks everyone for coming to hear us speak tonight. So we've got about an hour presentation that we're going to split between Rob and myself. Rob, you want to say the interviews?
Oh, yeah. I mean, you're welcome. And this experiment has been, very exciting for us. I see a lot of the people who are putting it together here in the crowd. So welcome, and yeah, we should let's talk about NASA's coolest mission ever.
So we're going to do a brief overview of the mission for those of you who aren't familiar with it, and for those online participating in the webcast. I'll talk a little bit how we're using the space station to facilitate this experiment. Rob's going to talk about the science that CAL will do and the science in general of low temperature physics. I'll talk a little bit about the implementation operations that the CAL mission has been going through for the past 5 years. Then we'll wrap up with some lessons learned and do Q&A. So we're your presenter this evening, and some of you know us, but obviously Rob is the atomic physicist, project scientist, and I have been the project manager for the past 5 years, and I'm a rocket scientist by training. The obvious difference is that I'm very short, Rob is very tall, and we'll both look really good in hairnuts. You'll see tons of hairnut pictures throughout this entire presentation. So now we're going to give you a short mission video that we've come up with for education, public outreach purposes. And we'll go to YouTube to play it, and hopefully you'll enjoy it. There are many things that we actually don't understand about matter. One thing, for example, would be gravity. We know that gravity exists, we can observe gravity, but people don't understand the quantum nature of gravity.
We have a very good theory of gravity. It's Albert Einstein's general theory of relativity. The unfortunate thing is it's not compatible with the very good theory that we have of quantum mechanics, of the subatomic particles and atoms and molecules and so on. And those two theories, they're not compatible. They conflict.
Roughly 68% of the universe is dark energy. About 27% makes up dark matter. So all we know is less than 5%. 95% of what surrounds us continues to be a mystery.
The way a Bose-Einstein condensate expands thermodynamically could potentially represent how the universe expanded when it first formed.
A Bose-Einstein condensate is a unique man-made quantum state of matter, which we can only obtain at the coldest temperatures and very high densities. It is actually a macroscopic ensemble of atoms that you can view with a camera, and these wispy clouds of atoms behave in very strange ways. They're no longer distinguishable as an individual particle. You really have to describe it more like atoms acting collectively as a wave.
What we're trying to do is to understand the fundamental nature of matter by basically continuing the quest to get to colder and colder temperatures.
It's not just lower temperatures, but it's also the fact that we want to study atoms, and we want to look at them for really long periods of time. And that is really only possible in microgravity.
On the Earth, you're limited by gravity. We have a limited amount of time once you let go of the atoms or weaken them that they will fall out of your trap and run into the limits of your experiment. So when we get to a microgravity environment, we can get to these long interrogation times in space.
We're going to be getting to a temperature regime which no one has ever seen before. So it's essentially the unknown what we're going to find in terms of how matter is going to behave at those temperatures.
The Cold Atom Laboratory is a journey to try to understand and to explore the unknown.
So that's our video. Okay, so now I'm going to talk a little bit about the CAL mission timeline and the CAL mission overview. So Rob and I actually worked together in the proposal back in roughly April of 2012, which is almost 5 years ago to the day. During the period of September of 2012 till about, I would say, about 2016, we were in sort of the detailed design fabrication phase. Now the mission is currently in the hardware integration phase, getting ready for its launch operations. The overall profile of how the mission works is that once the instrument is completed, in terms of being built and tested and assembled, it will be launched in a pressurized cargo vehicle. There's different ways to get up to the International Space Station. If you go inside of a pressurized cargo vehicle, your payload will actually always see a shirt sleeves environment. That means both in terms of pressure as well as temperatures. You don't see these sort of extremes of the vacuum environment that you might see during a typical launch. Our mission is scheduled to go up on a SpaceX vehicle, pressurized launch vehicle. So basically the pressurized vehicles allow payloads such as ours or such as life science payloads like rats to go up there and not get damaged as they ride up to space station. We'll talk a little bit more about that later. So after we get launched on the Falcon vehicle in the pressurized cargo vehicle, we dock with the International Space Station. We dock via an airlock. The astronauts then take us out of the Dragon capsule and then install us into something called an express rack, which is a standardized interface for payloads for space station. We'll talk about that a little bit more later. One of the advantages of CAL is that it's actually operated entirely remotely from the ground. So once the astronauts install the payload into what is called an express rack, we're able to operate the payload from JPL and do all of our science experiments remotely. And that minimizes the amount of time that the crew is required to interact with you, which is a good thing because crew time is sort of at a premium. And in terms of how we communicate with the payload, the space station communicates to TDRS, which then communicates down to NASA Marshall, which then communicates to JPL. So it's a relatively fast, almost real-time data link between JPL, NASA Marshall, TDRS to the space station. So the ride to space station is also slightly different than the typical free-flying spacecraft missions that JPL does. We go inside of a pressurized vehicle that you can see here, and payloads are basically launched in bags surrounded by foam. And so what that means is that the traditional launch vehicle environment, which can be very harsh on sensitive components, is somewhat mitigated by the use of foam inside of these bags. Once the bags are installed inside of the hatch, they're actually strapped into the interior of the cabin here, and this is how cowl will be installed basically into the pressurized cargo vehicle, and they're sort of strapped down, winched down. At that point, the launch occurs. We go up to space station, we dock with an airlock, and all this time the payload only sees essentially a short sleeves environment, which keeps it in a more safe condition than a traditional launch vehicle. The astronauts take us out of this bag, out of the foam, and install us into an express rack that you can see here. So where are we going to be on space station? So our payload is an interior payload, so it goes inside the habitable volume of the space station. And there's many different modules of the International Space Station. It's quite a large assembly, almost the size of a football field. But our goal, and Rob's going to talk about this a little bit later in terms of the science that we're trying to do, is we want to minimize our exposure to vibrations. We want to minimize our exposure to accelerations because the atom cloud that we create is very sensitive to that. So as a result, we want to be close to the center of mass of the space station. So we actually want to go inside the US module of space station where the accelerations and the vibrations are minimum, so we can get the best science possible to the coldest temperatures possible. What we also want to do is that we want to be aligned with the gravity vector, because some of the science that we're going to be doing is related to gravitational science, which means that we either have to be in the port or starboard location on space station. Now, on space station, since you're in a zero gravity environment, there really is no ceiling or floor, but there is an orientation relative to where the gravity vector is. So that defines basically which express racks we can go inside of. We are able to make use of a very convenient feature that space station has for the interior payloads, which is water cooling, that allows us to keep our system cold because we actually generate a lot of heat during the course of making the Bose-Einstein condensates. And we are able to occupy a relatively large volume of space. I'll talk about that later. But we roughly occupy the size of something the standard Earth-sized ice chest would be. We do operate the payload remotely from the ground, which is called sequence control, which once again minimizes crew involvement and crew time, which is at a premium. But we are very sensitive to all kinds of fields, electric fields, magnetic fields, gravitational fields. So we want to be in a location where we have a series of payload neighbors which minimize noise and magnetic interaction. So based off of that, this is a little bit of audience participation. So I want you to give me your input by a show of hands as who would be Cal's favorite space neighbor on board the International Space Station. So by a show of hands, would we want to be near Sunita Williams on the running machine? No? What about a space rat going around in a wheel? No? Lettuce. So yes, the lettuce is the selection. The reason for that is because the lettuce doesn't generate any vibrations, the lettuce doesn't generate any magnetic field. And the other way that we get around Sunita Williams or another astronaut exercising is that we only operate during the crew sleep period. So when they're not exercising, generating extra vibrations which we would feel inside the express rack, we actually operate Cal, which means that because the space station is operated on Houston time, the mission operators for Cal will have to be operating during sleep time in Houston to be able to minimize vibrations to the payload. Although the rat is cute, I think, in this particular situation. So if you were going up into space, what would you need? You would need air, water, power, and data, right? That makes sense if you're going into space. So our payload needs the exact same thing. Unfortunately for us, the Express Rack, which is the standardized interface for space station, provides just that. It provides 28-volt constant power to our payload, which actually keeps our pump going so we can maintain really low vacuum pressures. It provides air cooling, cooled air, which goes into the interior cavity here, which provides additional cooling. We also have access to a water cooling loop, which actually allows cold water to flow through heat exchangers that all of our electronics equipment is attached to, which allows us to cool it. It has, we don't make use of the vacuum supply on board because we have our own pump, but we also do have connection to Ethernet, just not because we're using Facebook, but because we're trying to connect and log into our payload. Basically, we're able to log into the Cal payload from the ground here at JPL and communicate with it back and forth, both to uplink data and commands, as well as to downlink data from the science instrument, which is our science data product. So what do? We go inside an express rack. So this is showing you the interior of the US module on space station. And each side here represents a different location of express rack. So this basically is an express rack region. And so they're constantly being used for payloads for different reasons. And so Cal will be integrated when other payloads come out. Cal can go in and we can operate it. And so we're going to make use of that water cooling loop. We're going to make use of air cooling to also keep us cool, constant 28-volt power, and then access to Ethernet, which allows us to communicate with Earth Earth and then from Earth back up to space station. And that's the way you make use of this interior laboratory on the space station. And what's so nice about this is that it's standardized. So we know what the interface is going to be ahead of time. We've designed the system to interface with it, and that is how CAL was built, to be specifically tailored to make use of the International Space Station. And the reason why this is different from some of other JPL's free-flying spacecraft mission is that we don't have to generate our own power, right? We don't need solar arrays because the space station already has them. We don't have to have our own cooling system with the use of radiators, for example, because we have access to the water cooling and the air cooling. So that's what makes space station a laboratory in space, and specifically to understand microgravity science that Rob is going to talk about in a lot more detail. So the other advantage of using the space station, or Rob's going to talk about it more from a science perspective, is that it allows us to come up with an instrument that can actually be repaired and upgraded on orbit. So that means that you can make it last for a really long time because the crew can come in there and do repairs, but you can also upgrade it to give you additional science capability on time. And so what we did here is we came up with a modular approach. So this is different from how systems are normally built at JPL, so that a human being could go in there and disassemble the instrument on orbit, take components of it out, replace individual boxes, put them back on again, and make it work without ever having any involvement from here at JPL or the experts at JPL. So that was an engineering challenge for us to be able to come up with this plug-and-play approach. And so you can see here how the system looks like in this plug-and-play fashion, where all hardware is mounted on individual heat exchanger plates, and then either lasers or electronics are in each one of those heat exchanger plates. So then the astronauts have to be trained on how to disconnect all the connections, whether they be fiber optic connections, water, or power or data connections, and how to reconnect them again. And so what we did to facilitate that is that we built a 3D model. And so we actually used 3D printing, which was a great use for it. So instead of building a full engineering version, we did it at relatively low cost, where we actually would print each component with a 3D printer with the correct hole pattern so that we could train the astronauts on how to put it together. And so we have this up in our ORU lab. It's called Orbit Replacement Unit Lab, up in Building 238 if you want to come take a look at it. And so this is actually what the CAL payload looks like. So there's a quad locker here and a single locker up here. So we have had several astronauts come out over the course of the past 3 years to work with us, both to teach us how to design an instrument that astronauts can interact with on orbit and easily disassemble on orbit, and also for us to teach them how to do the repairs and do the assembly and do the disassembly on orbit. So our first time we had astronaut Mike Barrett come out. This was at a much earlier stage in the CAL design process, and he basically taught us about which kind of connections were easy for them to do, which ones are hard, which were going to require special training. And then something that you probably wouldn't think about necessarily is the range of different potential astronauts, where you may have some astronauts with very big hands, like Mike Barrett had, and you may have some astronauts with really, really small hands, like I have really small hands. So each connector has to be thought with that in mind, so somebody can actually go in there and unscrew them and then retorque them to make them stronger again. So this was a more recent crew training that we had with astronaut Tom Marshburn and John Casada. This was just January, a few months ago. And here, this is essentially the final configuration of the instrument. And now we're actually developing the procedures whilst recording videos so that the astronaut crew can do these repairs when the time comes for them to do, which will maybe be 1 or 2 years into the on-orbit mission. And so we also do it to make estimates of how much time it takes to do these. So there's different stages that they'll have to do. The initial installation, which is relatively easy in terms of, there's hex bolts that you connect the quad locker to the express rack. But later on, when we do installations of lasers, that actually turns out to be a much more extensive sort of 1 to 2 day long repair period. So it is complicated, that's what they told us. In terms of the different types of payloads that are on space station, CAL is probably in the 80th to 90th percentile in terms of complexity because of the number of electrical connections, fiber optic connections, water connections, and data connections. So one other thing which is unique about CAL is the type of risk classification that it has. So those of you who already work at JPL and NASA know there's Class A, B, C, D missions. Class A, B missions are missions like the Curiosity rover, very expensive, multi-billion-dollar missions, one-way trip, it's got to work. And then Class C missions are a little bit less expensive, and then Class D missions are typically much cheaper missions, let's say CubeSat type missions, where it's okay for the thing not necessarily to work downstream. So even even though CAL has to work, we were able to adopt a Class D mission architecture because we have the ability to do repairs on orbit, and because we have the ability, if we really needed to bring the entire instrument down and repair it on the ground. So that allowed us to do things a little bit more cost effectively and time effectively. And one of the ways that we do that is with the use of commercial hardware. But of course, commercial hardware does have its challenges. For example, using Windows. We're all used to using Windows and crashes that you might have. And so our operating system actually does operate off of Windows. So we do have a concern, but we have the ability to reboot the system and even potentially do a hard reboot from the ground if we need to. But the reason why using commercial hardware is good is that the development time and cost associated with it has already been captured essentially by somebody else, and you're buying a part off the shelf. So we have, to the maximum extent possible, used commercial hardware in the design of CAL. So we also are allowed to accept more risk. And this means technical risk, it means schedule risk, and it means cost risk. And so it's always a trading game as to how much is acceptable. So if you can accept zero risk, your mission is going to cost a lot more money. If you can accept a lot of risk, your mission is going to be a lot cheaper, but there is chances when things don't go right that you'll have to spend more money and spend more time to fix them. And that's something that we have experienced over the years. But it's a gamble, you could think of it that way, but it's a way to make the mission more cost effective for both, for NASA. So the difficulty, of course, is that we have a very low budget, which means that we have a really small cookie jar that we have to work with, and we have to be really careful with how we spend the money. And it also means that you have a very small team. And what that really means is that each and every member of the team has had to wear multiple hats, play multiple roles. So how do you find the skill mix from a management perspective of somebody who can do scientific work, engineering work, integration and test work, as well as programmatic? It's actually very difficult. So whoever is working on a project like this actually has to have the ability to grow into many different aspects that they wouldn't have had to begin with. So part of the past 5-year journey for all of us is adopting a lot of roles and adopting a lot of capabilities that we didn't start off with. But I think we had a great team of people, which has gotten us to this point today. The other issue with Class D is that when you use commercial hardware, you're working with a capability-driven design. And what that means is the box that you've bought can only do what it can do. And so if it doesn't meet the specifications that it says it should, I'm buying, let's say, a computer which has this much memory and this much hard drive space, that's the capability you have to work within it. And so we had to do a lot of trades as the engineering community to make sure that we can fit within those constraints, having had to use commercial hardware, and of course the interfaces associated with space station, which we couldn't go beyond. So this is the final on-orbit configuration. We'll talk a little bit more about the guts of the instrument after the science talk that Rob's going to go through. But you can see this is an entire express rack. We occupy 4 lockers here, 1 locker here. Each one of these locker spaces could be a separate payload, but because we're a very large, complicated instrument, we actually had to occupy a total of 5 lockers. And so we call this the science instrument, which is where most of the science is going on, where our vacuum system is, and we'll talk a little bit more about the guts of that later on in the presentation. And then we have the power electronics locker, which houses a lot of our power distribution electronics. And so you can see we are a relatively big payload, but we needed that, and compared to what we started off with, which is an entire laboratory condensing into a size of a box, it's actually quite a challenge. So Rob's going to take it over from here.
Thanks, Anita. I'm going to talk a little bit about the science background for CAL. There's a number of grand themes that run and play out in science over many decades. For example, for several centuries, astronomers have been building ever bigger telescopes to look further and further back, in time and deeper out into the universe. Physicists for much of the past century have been building larger and larger particle accelerators to reach higher and higher intensities and to look again deeper and deeper into the heart of matter. I'm going to talk to you about another of the great themes of physics, the quest for ever colder temperatures. And especially I'm going to talk about the Cold Atom Lab, which represents the latest step in that journey towards absolute zero. One of the early pioneers in this field is the 19th century Scottish scientist, Sir James Dewar. He invented the famous Dewar flask, and he developed technologies to reach lower and lower temperatures, culminating in the ability to liquefy hydrogen at temperatures of about 20 degrees above Kelvin, 20 degrees above absolute zero. As an aside, scientists like to talk, physicists in particular, like to talk in Kelvin. It's a That's how we like to measure temperature. It's referenced to absolute zero, so 0 in Kelvin is absolute zero compared to 0 in Celsius, which is the melting point, the freezing point of water. The magnitude of each degree, a degree Kelvin and a degree Celsius, is the same. Anyhow, after Sir James Dewar's breakthroughs, following that, there was breakthroughs by Heinrich Onnes of Netherlands, who was the first person to liquefy helium, and soon after he discovered superconductivity, the ability in certain metals for currents to flow in the total absence of resistance. A few years later, during the infancy of the science of quantum mechanics, Bose and Einstein developed the theory of the Bose-Einstein Condensate, which we're going to spend much of the lecture talking about. And this is, theory told how certain types of particles would behave at temperatures very, very close to absolute zero. When it first came out, this theory, not too many people believed it really corresponded to anything physical. Even Einstein didn't really believe it. But as people started discovering the laws of superfluidity and superconductivity, they realized that it related to these investigations by Bose and Einstein. In the 1980s, techniques were made to cool atoms with lasers and reach temperatures of a millionth of a degree above absolute zero. And that rose a lot of excitement in the field that possibly we could finally observe this predicted state of matter. But it took another 10 years before Eric Cornell and Carl Wyman at the University of Colorado developed a new set of techniques that allowed them to finally observe this condensate. At the time, I was a postdoc. I had just started a little earlier than that in the lab of Bill Phillips. And as soon as this result came out, everybody in our lab, or at least a large fraction of us, sort of stopped what we were doing, and we started trying to make condensate machines. And this, not just our lab, but many labs around the world kind of joined into this rush. And that excitement has not let up. After 20 years, this has provided an extremely diverse area of physics. And we'll learn a little bit about some of that diversity as I go on in the talk. So James Dewar, of course, there's no way he could have predicted all these exciting things that would have come from this journey towards absolute zero. And as we kind of take the next step, kind of go a little bit closer and a little bit cooler temperatures, we have to expect that possibly nature will have some sort of surprises for us as well. Now, I should state, Sir James Dewar's contributions are very important, of course. But in truth, if the truth be told, he's actually not even the greatest inventor named James Dewar. That honor goes to the American inventor, James Alexander Dewar, who developed the Twinkie. So what is a Bose-Einstein condensate? To understand what a Bose-Einstein condensate is, we have to recall a few facts from the science of quantum mechanics. That's the science of very small objects, atoms and molecules and subatomic particles. And quantum mechanics teaches us that all matter has both a wave and a particle nature. That's associated with any quantum object. There's a wave function, and that the wavelength associated with that wave function is inversely proportional to the momentum of that particle, and hence inversely proportional to how fast it's moving. And that wave describes the probability of finding that particle in a particular location or a particular state. At high temperatures, atoms behave pretty much as particles. If you have a gas of molecules at room temperature, they're shooting around like bullets being fired out of a high-velocity rifle. And that classical behavior, you can just think of them as billiard balls. Their wavelengths are so short that we don't have to worry about quantum mechanics, and we can just think of them completely classically. As we reach colder temperatures, we reach the types of temperatures that we can reach with laser cooling, we start to see that quantum nature. The wavelengths get bigger and bigger, and it becomes more pronounced. And there's a transition that occurs at temperatures of a few tens of nanokelvin, where the wavelengths of neighboring atoms starts to overlap. Now, remember that wavelength of that atom tells the probability of finding the atom in a particular location. As soon as those wavelengths overlap, you can't tell which atom is which anymore. And you have to look into, you have to treat all these atoms are identical. And that was the insight that Bose and Einstein had come up with. So when you reach that point, the atoms undergo a phase transition. So phase transition is, you're all familiar with the transition from liquid water to ice. That's a type of phase transition, one state of matter to another state of matter. In this, in the Bose-Einstein condensation, that's a phase transition, a purely quantum phase transition, in which you transition into a state where a large fraction of the atoms are in the lowest possible energy level available to the state. And all of those atoms, their waves are perfectly in phase and coordinated with one another. That process of making BECs is now done routinely in hundreds, if not thousands, of labs around the world. And many people are reaching these types of temperatures. Going into microgravity, as we'll see, allows us to reach a new regime of temperatures that ultimately might get as low as a picoKelvin. That's a trillionth of a degree above absolute zero. At temperatures like that, the wavelength becomes on the order of about a millimeter. And that's just an astonishing thing, that a quantum wavelength could be that big. The one thing that people tend to know about quantum mechanics is that is the science of very small things, tiny things like atoms. But at these temperatures, these objects can actually be extended. This is the observation of our first Bose-Einstein condensate in a prototype of the CAL apparatus in our ground test bed up the hill. This is a series of pictures that we take. We shine a light on the atoms, and we look at the shadow cast by the atoms, and we can measure a density profile of the atoms. And this is 3 different measurements as we lower the temperature, bit by bit. And you see, as you go through this transition, as you pass this critical temperature, you very suddenly see this spike shoot up of nearly stationary atoms in the center of the cloud. So how do we get there? What are the techniques that we use to achieve these cold temperatures? We actually have a whole sequence. So there's a series of different techniques that we use. And we start with a technique called laser cooling. This, might surprise most people. We think of lasers as things that we can cut with or that we can weld with, even do nuclear fusion with lasers, right? So how can lasers make things colder? To understand how that works, we need to understand, 3 basic facts. The first is that we can push on things with light. Light carries momentum. You can imagine things like solar sails to zip around the universe, zip around the galaxy. We can imagine, and this is the same types of forces that produce the beautiful tails on comets. So light can push on objects. It carries momentum, and it can push on things. And then the next fact is that atoms are very particular in terms of the colors of light that they absorb. This is the spectra of rubidium. The very first spectra was actually taken by Robert Bunsen of Bunsen burner fame. He's the person that first discovered rubidium, I believe. Rubidium, if you try to shine light on rubidium, it'll only absorb at these very sharp lines. If you actually change the wavelength of the light that's impinging on a rubidium atom by a part in a million, it'll go from strongly absorbing to just barely absorbing at all, almost totally not interacting. So that's the second fact that we need to recall, is that the colors of light absorbed by an atom is very sharp lines. Is only very sharp lines. And then the third thing that we need to remember is that that color absorbed depends on the motion of the atom because of the Doppler effect. We're all sort of probably familiar with the fact that if you listen to an ambulance siren as it's moving towards you compared to when it's moving away from you, it sounds different. The reason it sounds different is that when it's moving towards you, those wavelengths are compressed. They're a little bit shorter. When it's moves away from you, those wavelengths are stretched and they're a little bit longer. Likewise, with light that's absorbed by an atom, if the atom is moving towards the source, it'll strongly absorb light of a slightly shorter wavelength, what's called blue-shifted light. And if it's moving away from a source, that light will be redshifted. It'll be the wavelength absorbed by the atoms will be longer. So we can put all those together and just understand laser cooling. When we want to cool atoms with lasers, we have a pair of lasers pointing on our gas of atoms. And we tune both of those lasers so that they're a little bit to the red, a little bit longer wavelength than those atoms really want to absorb. So they're a little bit more red colored than the color the atoms really want to absorb at. So if an atom's just sitting at rest, it barely feels the force from either of those atoms. But if the atom happens to be moving towards one of these lasers, because of the Doppler shift, it will see that light shifted towards the light that it wants to absorb at. So it'll more strongly absorb from this laser beam. That'll provide a force on the atom, which will slow it down. We can extend this into 3 dimensions very easily, with 6 beams kind of coming from all different directions. And this proves just amazingly effective, more than one could kind of possibly hope for. And the most amazing thing about this probably is the fact that we can achieve these temperatures as cold as a few millionths of a degree above absolute zero in an amazingly routine manner. In thousands of labs around the world, scientists can walk into that lab and literally it's almost a flick of a switch, and you have a sample of atoms at a few millionths of a degree above absolute zero. Now, I said at the beginning that most people, when they think about shining lasers at things, this is not just laymen, but scientists, when you tell them that, if they're not in this field, would imagine that things would get hotter, right? And it's true, it actually is true. There is a heating mechanism, and to actually figure out the temperature, where we get this millionth of a degree above absolute zero, we have to balance heating effect from the lasers with this very powerful cooling effect, and that leads to temperatures in this range. If we want to go better, if we want to get colder, we have to turn the lasers off. And so the way we do that is we use a technique called evaporative cooling. We put the atoms into a magnetic trap. We can prepare the atoms in a state where they act like a little bar magnet. So they have north side and a south side, and they can be pushed around with magnetic fields. And if you can set up your magnetic field so that there's a minimum in that field, the atoms will be trapped there and they'll be attracted to that minimum. In Cal, we produce those fields with something called an atom chip. It's a piece of silicon, and it's got wires printed on it, just little metal wires, and we run currents through those wires, and that produces a magnetic field that we can use to trap the atoms. Inside that magnetic trap, now the atoms, it's like they were inside a cup. And the cold atoms are kind of bouncing around the bottom. The hot atoms kind of make it up, higher and higher up the walls. The cold ones are down here, the hot ones kind of bounce up like this. And we can selectively pull off just those hottest atoms by shining radio frequency or microwave frequencies at just the right, if we tune it to just the right frequency, we can just pull off just these hot atoms. The rest of the atoms will cool down and equilibrate at much lower temperatures. It's something like blowing on a cup of coffee. When you blow on a cup of coffee, you're helping the hottest atoms to escape from the liquid, and that brings down the whole temperature of the coffee. So how do we measure temperature? There's several actual methods that we can use to measure temperature, and we can compare them to make sure that we're getting everything right. But the simplest way to measure temperature is simply to turn off our magnetic fields and release those atoms. So the atoms are sitting there in a cup, and we finished cooling them, and they're pretty cold, and we want to see how cold they are. We can just very quickly turn off that magnetic field. When we do so, those atoms, that cloud of atoms starts to expand. And the hottest atoms, move the furthest and the fastest, and the cold ones are left behind. We can just wait a little while, and then we take a quick snapshot of what's going on with the atoms. And just by measuring the size of this cloud, we can tell the difference between a hot cloud and a cold cloud. Again, these images are taken by shining light on the atoms and looking at the shadow cast by those atoms on a camera. This evaporative cooling technique is used in many labs around the world. We want to be the coldest spot in the universe, or close to it. And so we use some other techniques that kind of fall into the realm of what I call advanced cooling to get even colder temperatures. And the first one I'm going to talk about is something that goes by the rather exotic name of delta kick cooling. It acts really more like a freeze ray. So I like to call it a freeze ray. But what we do is we just let go of our atoms, and they expand just like we were going to measure the temperature, right? And the hottest atoms, after a little while, have moved the furthest, and the cold atoms are left behind. We can then snap on another magnetic potential for just an instant, and we can, if we turn that magnetic field to just the right strength and in the right position, we can we can provide each of these atoms a little bit of a kick, such that the atoms that are far away here, far over here, and the hottest ones receive the biggest kick, and the atoms that are left behind receive a much smaller kick. And so they're all kind of instantly sort of frozen into space. Another technique that we can use is a technique called adiabatic cooling, where we just let that cup, that magnetic trap, we just get it weaker and weaker and weaker. And if we do that slowly enough, as that gas expands, it cools down. This is similar to when you spray on an aerosol can, and the aerosol can gets colder as you do that. This again can be done on the ground, and we do it fairly routinely to try to lower our temperatures that we see. But you're limited in how well you can do it on the ground. On the ground, you always have to support against gravity. You have to hold the thing up against gravity. So that limits how weak you can make those traps, and it limits how well you can use this technique. We have a number of PIs on this project. These are external folks that are doing science investigations. The first one I'm going to mention is Cass Sackett, because he is actually helping us trying to research the ultimate limits of this adiabatic cooling technique. So we combine all these techniques into all these different stages of cooling, different types of techniques into the cold atom lab, and you've seen pictures of it that Anita showed. It's a mini lab in space. The idea is that we give researchers a large suite of tools, many of the same tools that they use in their own labs on Earth, and we try to put those into this facility. We have, for example, the ability to trap two different species of atoms, rubidium and potassium, and two of the different potassium isotopes as well. We have the ability to look at the atoms from two different directions, and with high and low resolution. We can prepare a variety of states, and we have ability to actually tune their interactions, and we'll talk more about that in a bit. But the basic idea is to kind of give scientists just a versatile set of tools that they can carry out just a wide range of very different experiments. As we talk about some of the experiments that our PIs are going to do, you'll kind of get a sense of the breadth, both of the field and what we're able to do with the cold atom lab. Why do we do this in microgravity? So the kind of dream of atomic physics is, for centuries it's been this way, that we want to create a sample of atoms, and we want to just have them sit there motionless while we look at them for as long as we want to, right? So we want them completely unconfined. We don't want any magnetic fields or lightweight fields on them, so that those would also disturb them a little bit. We don't want them to bouncing into walls and things like that. We just want them to just sit there, just to stay put. And we want to, we want to look at them for very long periods of time. If you try to do this on Earth, so you can get pretty cold temperatures on Earth, but if you try to just kind of let the atoms go, they'll go plop to the bottom of your vacuum chamber, and you'll get, a fraction of a second typically is your time to look at them. And as people make tricks to get a little bit longer time, but you're sort of fundamentally limited in how much time you can look at them. In Cal, in microgravity, these atoms should just hang around for, we hope to something like 5 seconds. But one of the ideas behind Cal is that, it can be improved. We'll have follow-on missions, and these things can be improved upon. Ultimately, the limits could be hundreds of seconds. So I started, thinking about Cal, back in, as soon as I came to JPL. It's a couple of years after being a postdoc, and I've been working on, almost my whole career. Even right from the beginning, even before the space station had been put together, just a couple of years after BEC had been discovered, I was trying to pitch this idea that we could have this BEC lab up there. And so this project, me and my colleagues have been developing, a lot of that technology. Our effort, got off strong for a few years, and then we, because of issues with, with the space station program, we kind of stopped doing this type of research for a while. The Europeans, in particular, German groups, have continued this and have had a very steady, long, and very successful program, actually preparing Bose condensates and studying them in microgravity. First in drop tower experiments, where they have these 200-meter towers and they drop the whole apparatus to get a few seconds of microgravity. And also in sound and rocket experiments, where they can get hundreds of seconds of microgravity. The goal in Cal, though, is to just be up there and have hours and upon hours that you can tweak things and fiddle with things and get them just right, and have much longer duration of microgravity. One of the technologies, and it's sort of the killer app for ultra-cold atoms in space, is a technique called atom interferometry. Some of our most sensitive measurements are made with light interferometers. Probably the most famous is the LIGO detector. That's light laser interferometry gravitational observatory. And there's 2 of these, one in Washington and one in Louisiana. And last year they observed the first signal of a gravitational wave formed by 2 combining black holes. These types of interferometers use physical beam splitters and mirrors to interfere beams of light to make these exquisitely sensitive measurements. An atom interferometer is a little, does kind of the opposite. We actually use beams of light to split up atomic waves, and then other beams to reflect them and recombine them. So we have, atoms coming into this apparatus. We shine on a laser beam. When we shine that laser beam, we can arrange its strength so that the atom has a 50% chance of going this way and a 50% chance of going that way. Quantum mechanics says, if you haven't made a measurement, you have to assume it's in both at the same time. So the atom is actually physically in 2 different places at exactly the same time. That's a little mind-boggling if you think of atoms as particles. It's not so strange if you think of an atom as a wave, though, right? If you get at the beach and you see a wave kind of coming into the beach, it's spread out, right? And if you have a wall that juts out into the ocean, half of the wave can go on one side, half of the wave can go on the other side. That's not, such a big deal. The thing to wrap your head around is, how can something be a wave and a particle at the same time? How can these things actually be in 2 places at once? But we then recombine these waves, and when they recombine, they interfere. So this is a very ubiquitous process with any type of wave phenomenon. that when you combine two waves, they will either cancel each other's out or they will enhance each other by either what's called constructive or destructive interference. So they produce fringes, and by monitoring these fringes, we can make these very sensitive measurements. Already on the ground, we get measurements of things like accelerations and rotations and gravity that are as good as you can make with almost any other means of making them. But the fantastic thing is, how much better these things get when we go into space. When we go into space, we get to look at the atoms for much longer. So on Earth, the way we do these experiments typically is we toss the atoms in the air, and they have about a half a second or so that we can make an interferometer. We have one of those here at JPL. In space, though, we can get, in Cal, we'll get a couple of seconds, but in future missions, we might even get hundreds of seconds. For some types of measurements, for example, for gravity or an acceleration measurement, the sensitivity of that measurement goes as the square of the amount of time that you have to look at it. So you can have this huge possibility of making incredible types of measurements. These types of instruments will yield this, basically a new generation of exquisitely sensitive quantum sensors. They can be used for things like testing fundamental physics, some of the fundamental ideas of Einstein and some of the ideas behind things like dark energy. But they can also be used for real-world applications. We can use them to monitor Earth's gravity. So JPL has a mission now called the GRACE mission that monitors Earth's gravity using a pair of satellites that orbit around the Earth. And that can measure things, like can weigh the ice sheets. We have a follow-on mission that's going to go on called GRACE follow-on. But in the future, we might use these types of sensors with a little bit more development. These might be very competitive or significantly improved over what we can measure. That allows you to make very important measurements relating to climate, but we might also fly these around some planet and look for resources that future astronauts might want to use, or we might search for oceans under Europa and all kinds of interesting possibilities. And that brings up to the basic idea of various applications of absolute zero. One of my favorites has always been the atom laser. An atom laser is a source of coherent matter waves, just like a laser is a source of coherent light waves. And these were discovered and been observed on the ground. This is one that we observed something like 10 years ago. And another scientist was the first had observed them significantly longer before that. But these, they don't do that much on the ground, because it's very strongly perturbed by gravity. In space, we might imagine, a whole world of applications for them in atom optics and things like matter wave holography. Probably one of the killer applications for them would be as a source for an atom interferometer. I now want to kind of turn to some of the Cal science, some of the science investigations by our principal investigators. So we put this facility together with all these kind of standard tools, and then we invited scientists to come up with proposals of how to do it. And we were very impressed with the quality of the proposals, the quality of the science team. Really, Cal has probably one of the most prestigious science teams that NASA's put together for any mission. This is a study of few-body physics in microgravity. It's led by Eric Cornell. He's one of the people on the team that first made the first Bose condensate. Peter Engels works with him, does a lot of the heavy lifting on this particular project. Debbie Jin started with this project, and we were very honored to have her. She's a very prominent scientist, really the leading expert in the world on cooling potassium, and she was the first person to make a fermionic condensate, and she was a MacArthur Fellow. Tragically, she died last year, and we're all sort of very sad about that. This experiment searches for sort of universal features in the way a few bodies, 3, 4, 5, come together and collide, and it looks for bound states between those molecules. And because it's universal, you get the same behavior with gases of potassium as you would with a gas of, say, strontium or something like that. Or even in some cases, you can see universal behavior between how atoms behave and things like neutrons and quarks behave. What's very profound about these types of experiments are they can give us some insight into how complexity arises in the universe. So if we listen to our particle physicist friends, they are convinced that the universe is very simple. There's just a few fundamental particles, and they obey just a few simple rules. And they also tell us that the only thing that ever happens in the universe is these fundamental particles bounce off of each other as they collide. So how can you get from that simple physics that we believe, we don't know for sure because we don't yet have that final theory of physics, but one of the driving principles of theoretical physics is that physics is simple, and we always look for these simple solutions. But so what could lead to all the complexity that we see around us? Galaxies and forests and trees and symphonies and things like that. How can that kind of complexity arise from very simple underlying physics? And we can kind of get an insight into that by looking at this realm of few body physics with 3, 4, 5 atoms, and then try to work our way up to understanding more complex systems. Another team, and this team features 2 other Nobel laureates, Wolfgang Ketterle, who, independent of Eric Cornell and Carl Weinman, developed one of the very first Bose-Condensate apparatuses and did a number of landmark studies with them. And Bill Phillips, who was one of the pioneers of laser cooling, are both working with Nick Bigelow, who is heading a fairly large consortium, lots of different, very prominent scientists. And in particular, Holger Mueller is kind of doing the most of the thinking about this one particular experiment. So he has a number of ideas of how to test Einstein using atom interferometers and in space. And one of the ideas is to just look at, kind of repeat Galileo's famous, we don't know if he actually did it or not, experiment where he drops 2 balls off of made out of different material off of the Leaning Tower of Pisa and shows that they fall at the same rate. And the idea is, can we drop potassium atom and a rubidium atom? We're going to drop them, up on the space station, and they'll fall for a couple of seconds. And during that time, in orbit, they'll go about 8 miles around the Earth. And at the end of that, we can measure them to within sort of a fraction of the wavelength of light, about 100 nanometers or so with an atom interferometer. The importance of this is Einstein's theory is predicated on gravity acting on all particles exactly the same. And so if we can see a difference, that might point the way towards some theories beyond Einstein. Jason Williams of JPL has a really nice study planned of what we call halo molecules. So one of the really interesting things about ultra-cold atoms is that we have techniques to very precisely control how strongly they interact. So if you just look at a gas, atoms in an ordinary gas, they may repel each other, they may be attracted to each other by a little bit or stronger. But with these types of systems, we can actually control that. We can make them attract very strongly, we can make them attract very weakly, we can make them repel or very strongly or very weakly. By making the interactions very, very low, we can actually observe what we call halo molecules. And these are the most weakly bound of any kind of diatomic molecules. They can be on the order of a micron, which is an astonishingly large size compared to typical molecules that we see. And Jason has a number of ideas of things that you can study with this very interesting system. We have another team that is trying to study, led by Nathan Lundblad of Bates College, which is trying to study bubble quantum states. These are spherical quantum states, so hollow bubbles, a condensate kind of spreading around that type of trap. We know how to produce a potential that would make a bubble, but if we try to do that on Earth, this is what we find. This is actual data that we took in our test bed, trying to use parameters that that represented what Nathan was interested in doing. And what you see, instead of having this, you have this circular potential, but all the atoms sit down at the bottom, and it's so not terribly interesting. In microgravity, they would spread out over an ellipsoid. And it's a very complex system, lots of possibilities of studying interactions and excitations and maybe putting in multiple atoms and watching them how they interfere and things like that. It'll be a very rich set of physics from this state, which can only be observed in microgravity. But as Anita pointed out, we've designed CAL to be repairable by the astronauts, and it's also upgradable. So we can bring in new technologies, new types of lasers. We can bring in a whole new vacuum system with new geometries for our magnetic traps and new ways to aim lasers into that trap. Or put other types of systems in it. So it really leads to sort of a limitless potential for possible future investigations. And with that, I will turn it back over to Anita.
So I'm going to wrap it up now. We're showing you some more fun pictures of the hardware that we developed and the build process. But first, I wanted to start off with the real challenge for our overall engineering implementation was to be able to condense something which takes the size of an entire laboratory, and I'm sure you've all worked or seen laboratories, and to condense it into something the size of a box around this big. And so our ground test bed, which is up the hill in building 298 at JPL, basically is that laboratory. So you can see this entire one side of the room is electronics, lasers, optics, computer system, and then on the other side of the lab is where we have the vacuum system that actually makes it with some free space optics. So all of that had to be condensed. So we had to make specific engineering decisions and technology choices to facilitate being able to fit in that small space so that we could go inside of space station. And so the large way that we did that is by the use of the atom chip-based vacuum system that Rob already spoke about, and the use of fiber optics, because by using fiber optics, you eliminate the need to have free space optics, which allows you to condense into a smaller volume. I'll talk about this in a little bit more detail. So just to go through some of the enabling technologies, the first one is the use of our atom chip-based vacuum system here. So you can see the system. It consists of basically 2 glass cells. These are under ultra-high vacuum, and then a metallic structure that goes around it. And the laser light is basically shined into the lower glass cell for the 2D Mott region and to the upper glass cell for the 3D Mott region. And so the challenge of this, of course, for anyone here who has a mechanical background, is that glass obviously is a very sensitive structure. If the glass breaks, number one, you lose your vacuum, and number two, you don't want to have pieces of glass floating around on space stations. We had to make sure that we had a robust enough design so that we could handle the launch loads going up to space station, as well as the handling associated with assembling the vacuum system to the final configuration. And so what you can see here is the buildup of the vacuum system inside something called an optical bench. So the bulk of our system is an optomechanical assembly. So we have to have a way to route the laser light, which is coming through these fiber optics, specifically into locations in the 2D Mott region down here and the 3D Mott region down there. And if those laser beams are not perfectly aligned, basically within fractions of a millimeter, you're not able to do the laser cooling. So you have to come up with a very rigid mechanical structure, an optomechanical bench, to make sure that never shifts over time, either due to the initial exposure to launch loads or over time due to creep, as it sits there on orbit for many, many years on end. And so this is the system we came up with, and this is in its partially assembled state, but tucked inside of here is the vacuum system. So once it goes in, it doesn't come out. The other enabling technology was the use of external cavity diode lasers, which had fiber optic outputs. And so these were essentially commercially available lasers. We had to customize them a bit from a packaging perspective, but we were able to put all 6 lasers on a single heat exchanger plate. So we have 3 for rubidium, 3 for potassium, and the fiber optics get routed and go into the assembly you see here, which gives you the laser cooling in the upper region, in the lower region, and in the upper region. So those were 2 key pieces of enabling technology to fit in this small constrained space to be able to go on space station. The other piece of technology that we had to develop custom at JPL was our electronics, essentially low noise current driver assemblies. Normally, electronics that we would use to control these lasers basically are about this big for just one of them. So you can imagine having to have that times a total of 6 lasers lasers times another 2 tapered amplifiers, you've already blown your volume allocation. So we have to come up with our own uniquely designed current driver electronics. And they basically fit inside the region of a tiny little box. And so that was a large engineering challenge to be able to give us the performance that we needed in the space that we needed with the power levels that we needed. So this is going to show you sort of the build-up, and so I do like to show this for people who are, I guess there's not a lot of kids in the audience, but from an engineering perspective, first you have to come up with a conceptual design, then you come up with engineering requirements, and then you come up with a detailed design. So what you can see here is a CAD model of our vacuum system embedded inside this mechanical structure with a magnetic shield that goes around it. So this is the design that we came up with. You analyze this design to make sure that it can handle all of the spacecraft environments that you're going to see, and it's going to give you the performance that you need. And then you go off and you actually build it. So you can see a partial build state here. The vacuum system is tucked inside of here. This is the optical mechanical bench that you see around. These copper-looking pieces are actually copper conductive straps so that you can cool the system. It actually gets very, very hot. And so you have a water cooling loop that goes around here, throwing cold water through it from the space station, which then all the heat from inside of here gets conducted through these copper straps into this water cooling loop. So that's how we're able to keep something which is generating a lot of heat inside of a tight box so that it doesn't get too hot. So this is sort of the engineering challenge of being able to get the heat out and get the performance that you need. And then also, as we're going around in orbit on space station, we're going around the Earth. And so when you're in a laboratory environment on Earth, the magnetic field is essentially always the same. But when you're going around in orbit of the Earth on space station, the magnetic field is constantly changing. And so we had to have a way to sort of dampen out the changing magnetic field. So we developed something called a magnetic shield. So for those of you who are a Star Trek fan, it's shields up, but our shields are always up. And we're, of course, just damping out small changes in the magnetic field as opposed to photon torpedoes. But we used a technology called mu shield, which basically took it down by about almost 2 orders of magnitude, so that we're less, now we're no longer having to see these large fluctuations in the magnetic shield as we go around the Earth magnetic field as we go around the Earth every 90 minutes. And so this is the final configuration you can see here assembled, ready for integration into the overall quad locker structure. So the second part of the instrument is called the science instrument. And so this is the quad locker. You can see it here at the design stage. All of this, of course, done in CAD originally. This is where you see the science module, which is that magnetically shielded vacuum assembly. And then these are electronics. This is called the laser frequency lock assembly. This is the plate where all the lasers and the tapered amplifiers are on, and then another set of current driver electronics. And so all of this gets tucked away into this pretty tightly constrained space. All of the electrical connections are made. The water connections are made here and here. The fiber optic connections are made between the lasers and the science module, and this is the system that gets designed. And in terms of how does it get installed into the express track, it's pretty simple. We have these 2 little rails up here. A hex bolt goes all the way through. The astronauts screw it in these 2 locations, and you're done. Because when you're in a microgravity, zero gravity environment, you don't have to worry about this heavy, 200 kilogram box hulking around. It's essentially, in free fall floating around. So it's pretty easy to install. The worst loads that it experiences are either on the ground or during the ride up in the launch vehicle. And so here you can see the final flight configuration in our clean room at JPL. And so what you don't see here is the science module, because that's still sitting in a different clean room right now, but you can see installed here our flight computer, the laser, the common mode filter, which is another piece of electronics, and the lasers that would go right over here. And up here is our power electronics locker. So I'll show you one more picture of that. So this was the design, the detailed design of what the power electronics locker would look like. You can see the top cover is removed here. Once again, all of our equipment is designed for the astronauts to be able to disassemble on an orbit and take out the different boxes. So this is the design, and this is the actual build. This was during an intermediate build process, and this is the final configuration here. And you can see it's got its nice paint job so that it fits in with everything else on space station. And so, it takes a long time to go from the original design all the way to the fully integrated system, which on our order was around 5 years in total. So then we're in the integration and test phase. So we had a really nice article written recently by the Pasadena Star. So we got a bunch of fun pictures if you want to see them. I think I've included a lot of these in the presentations. And so the final phase of any spacecraft mission is integration and test, where you take all your flight hardware, you put it together, you plug it in, and you start testing it and get your system level testing performance. So that's the stage that the mission is in right now, where things are being integrated in our clean room, and we're going through and testing out all the interfaces between the different equipment. Software, electronics, lasers, vacuum system. For us, that's what it is. And so we did take this one picture, which I liked, which is the shot for our new album cover, Ice Ice Baby. I hope you get that. If you're too young, you won't get that. So our mission timeline, so our plan is to go on SpaceX, and so what that means is that we deliver basically 16 days before launch. We want to hold on to the payload for as long as possible, basically so that we can keep it safe, and also so that we can keep the power on. So the way we maintain our vacuum is with something called an ion pump. So it's not a traditional mechanical pump, it's basically a cathode and anode, high voltage between it, and whatever atoms are still floating around there get ionized and they stick to the plates. And so we want to keep the power going on for as long as possible because it keeps our vacuum level really low. So we're able to turn it over pretty late, which is 16 days before launch. It gets turned over, it gets put inside of something called a clamshell, which is basically a big piece of foam all tucked in so that it's protected from the really nasty vibrations of the launch. It's then installed into the Dragon capsule, which takes around 13 days, where they strap it in with the straps that I showed you early. You always have to account for a potential launch delay, so we put 2 days in for that. It takes about 5 days going up on the rocket to get to space station. We then dock, berth. It should be taken out in about 1 day's time, and the install we estimate to take around 2 days. And at that point, the power on the express rack is turned on, and then we start communicating with it, and we start doing our science from the ground, which starts off with initial calibrations, and then all the science investigations, which follow. And so when you add all that up, it adds up to 26 days, and this means we have 26 days with no power, no ability to communicate with it, but we think we have plenty of margin on that, so it should be okay. So how are we going to do operations? And so the operations are all remote. We have our laboratory here. It's called our ground test bed. So the test bed is where we generate our flight software sequences. We test them out in a laboratory environment first to make sure that they'll work. Then we transfer them over to the operations center. We're going to be in building 264, first floor, Earth Science Mission Operations Center. They're uploaded to Cal via Ethernet. It's called KU IP services. And then the data comes back down, which is in the form of images, which are reduced by the scientists, and they're able to collect the science data off of them to continue doing our experiments. That data is then sent to the individual PIs, who then will go off and process them further. So in terms of the overall operation phases for Cal, we start off with the initial installation. This is done by the crew. Really does consist of unpacking it from the clamshell, installing that quad locker or the science instrument, installing the pyroelectronics locker, making fiber optic connections between the two of them, making the water connections to the express rack, making the power connections to 28-volt DC power supply, and then it's essentially good to go. We have an initial checkout phase where we want to make sure that we can communicate uplink commands to the instrument and then receive the data via downlink via the KU IP services connection. We're going to take about 6 weeks to do that initial check-in. Then we're going to do validation, which is where Rob and his team are going to be going through testing out all the capabilities of the instrument on orbit to make sure everything's working and to sort of calibrate to understand how things are going to perform, because the environment on space station is going to be very different from the environment on the ground in two fundamental ways. One, on the ground, we have 1G. Up in orbit, we're going to have, essentially zero gravity, so things are going to behave very differently, right? So the cloud may normally have been in one location, which means they're going to have to tweak magnetic fields. That all needs to be calibrated into the operational sequence once we get up there. Of course, the magnetic field is going to be different, which also affects the way they're going to generate the sequences. And the thermal environment is going to be very different, because when you're in a microgravity environment, you don't have natural convection. So you basically have hot spots. So you have to be able to move stuff. You either have to have forced convection by using fans or the water cooling loop, but it's going to change our thermal environment. So at JPL, we have a mantra which we call test as you fly, but sometimes you have test as you fly exceptions. So for us, our exceptions are gravity, and then the thermal environment associated with that, and the change in the magnetic field that we see between here on Earth and what we'll see varying as we go around on orbit on space station. Then we shift over to the science operations phase. And we have almost 3 years of science operations to go through our 5 PI teams, and we'll probably do times where they operate for a month or two, and then another team comes in, and they can recycle back. But we've got plenty of margin in the system. Now, in all of this, we're going to be reading the telemetry that comes back from the instrument. So if something shows us that one of the lasers is starting to degrade, for example, we do have the ability to have the astronauts go in there and replace the laser. So this is the reason why it's an advantage to be able to be on space station, where you have the ability to do these repairs. And we're actually flying up spare parts. So even though we have the primary instrument that gets shipped up in a clamshell, we also have a bag of spare parts, which is extra lasers, extra tapered amplifiers, and extra computer cards. So the radiation environment in low Earth orbit where space station is pretty benign, but you do still have the chance of getting high energy particles that could potentially come and hit an electronics card that you're worried about. So we also have spare parts that we can shift out those electronics cards if we need to, and the astronauts will do that for us as well. So this one we probably won't go through. This is kind of the details of what the science operations look like a day in the life of operating CAL. And so I think we wanted to sum up with our lessons learned from the mission overall the past 5 years. You want to engage the science community early so you can understand what they need, how they want to operate it, what capabilities they need to be able to do it. You really want to understand how do you translate science requirements into engineering requirements and give you sufficient margin on the engineering side to give you the science that you need. That's very difficult to do when you've never done something like this before. So CAL's kind of the first of its kind, going from very complex science requirements to very complex engineering requirements. If you are going to use new technology, you want to test it early so that if you can find any kinks in the system and fix them, that of course suggests that you have enough schedule to do it. It can always be a little tricky for Class D missions. So use of commercial hardware is convenient because it already exists, but it's also very difficult because sometimes commercial hardware doesn't meet its specification value, and then you're limited to the actual capability of that commercial hardware. So, and there's also a lot of variability. So I'm sure you've all bought TVs over time. One TV comes out the box, fries the next day. Another TV lasts for 15 years. So that's one of the risks associated with using commercial technology. So you also want to understand your ISS interfaces really well. So that comes to systems engineering, which is another discipline of engineering that the space community has to use. It basically tells you how do you interface with hardware from a mechanical perspective, thermal perspective, pretty much in every way. Now, the unique thing about operating something inside of space station is understanding the safety requirements working with the crew. It imposes a whole new set of requirements which most missions at JPL don't have to deal with. Things such as touch temperature. The thing can't get too hot so the astronauts don't injure their hands. How sharp are the edges so the astronauts don't injure their skin or their fingers. Ways that fasteners have to have some kind of tether associated with them or have to be captive fasteners so they can't go float around, right? Because you don't want someone to accidentally swallow something. So it actually brings about a whole another paradigm of doing engineering when people are involved in space as opposed to a free-flying spacecraft. And ultimately, it really does take a village, and this goes for every mission at JPL, a diversity of technical backgrounds and capabilities to be able to pull off engineering such a complicated system. But if everyone's interested in it and loves what they're doing, it ends up working out quite well. So I think that wraps it up. We're going to do Q&A now. And so we've got some fun pictures of the team. This is the engineering team listed here, and I think at least 7 of them are in the audience right now. So thank you very much. So how do we take questions?
Yeah, if there are any questions, please step up to one of the mics here.
Everyone's too afraid.
Yes. Can you tell me roughly what kind of quantities of the materials like the potassium are you using? Is it micrograms or pounds?
It's a fraction of a million. Yeah, I think it's 100 micrograms or something like that that comes inside a dispenser.
And is that something that can be added later from the crew?
It actually is that's one of the few things that actually could run out. These systems usually last for 3 or 4 years, so we think we'll last the 3 years with the amount that we have. But that is what we call a consumable. It's something that would run out. If it ran out, we'd have to replace the whole vacuum system.
I see. Thank you.
Yeah.
Hello. Using the pico scale, in effect, does CAL fluctuate in temperature from the time it's launched to the time it reaches the ISS?
Yeah. So one of the amazing things about this technology, the atom chip that we're talking about, is this cold sample that's at these temperatures at nanokelvin or below is held just 100 microns, which is like the width of a hair, below the size of that atom chip. And the rest of the apparatus is all room temperature. So and it might change a little bit, get warmer or colder through different cycles. But the atoms are isolated from that and don't see that. Those kinds of
If that does occur, though, is there any way to possibly fix the problem?
So I would say from a thermal perspective, the most difficult thermal environment will be when it's actually operating. So when it's non-operational, it isn't really dissipating any heat. So the most extreme thermal environment will be when it's operating.
Thank you.
Great talk. Thank you so much. Is it okay to ask 3 questions?
That's fine.
First one, is there any possibility, assumingly the current draw is really minimal, is there any possibility of using an external capacitor to maintain charge on the plates during the 29 days where it's being integrated?
We did do a trade actually to use a battery to keep that going, and we decided that that added so much cost and complexity that it's easier just to not use it. But you could actually use a battery to keep it charged up. But we're pretty insensitive to the 26 days in terms of vacuum pressure changing. But.
Yeah, it's not a huge risk. It kind of, if your pressure gets too high, it just takes a while. You lose time to pull it back down to the temperatures, pressures that we need.
Cool. Second question, can you comment a little bit about what are the underlying principles for quantum bubbles to assume a elliptical cross-section
Yeah.
as opposed to spherical?
It's actually very, we make this trap that has this geometry. It's actually very, if we would actually like to make them spherical, we'd like to make them equal strengths in all the different directions, but that's actually fairly difficult with our system, and they tend to be more football shaped, I guess.
And then third question, can you comment a little bit about when you get to intended operating temperature, you indicated that the summation wavelengths are on the order of a millimeter.
Yeah.
How does laser tuning work as you proceed down the wavelength dimension changes of? We've turned the laser coolant off,
at a point of temperatures of millionths of a degree. So those last stages just have the magnetic trapping involved. And that wavelength really tells us something about the probability of finding an atom in a particular location, I guess.
Thank you.
Yeah.
Hi. You mentioned earlier how you were using like a Windows operating system to run the software on this machine. I was just curious if you could expand on that. Like, what kind of Windows are you using as a very customized version, I'm assuming, or?
So we actually use a lot of National Instruments hardware. So the computer that we're using is a National Instruments PXI chassis, and we run LabVIEW off of it. And so LabVIEW has to operate, I think it's Windows. Is it Windows NT? I forget. Is it Windows 98 or NT?
Windows RT, I think.
RT. Well, so we're actually because we're using LabVIEW, we have to use Windows to run it. So we don't have a choice. So we're using commercial software as well.
Oh, okay. Thank you.
How do you actually measure these low temperatures?
It really is this idea of just releasing the atoms. And so what is temperature? It's just the average random motion of molecules or atoms. And so if we just let the atoms go, the hot ones will move faster and further than the cold ones. And so just by measuring the size of the cloud, we can measure what its temperature is.
Hi, I just had another question. Do you believe Cal is successful enough that it would aid in explanations to strange phenomena such as the Boomerang Nebula, which is currently the coldest place in the universe?
So there are these, so there's lots of claims to coldest place in the universe, and that's, I think, one of the coldest naturally occurring ones. I don't actually think that we would be provide any insights into that situation.
What do you hope to discover? Any reasonable expectation?
Well, so we've talked about these sets of systems that we can kind of make and probe. Ultimately, these types of experiments, and it might not be Cal, but some follow-on to Cal, I think can kind of push Einstein to the limit, kind of, as well as he can be tested. It's not clear that it'll be good enough to find that he's wrong. So as we said in the video, the general theory of relativity, it's a very good theory. It stands up to every test that we put it to. But it's not compatible with our ideas about how quantum mechanics work, the science. And that, again, that survives every test that we can put that to. They don't usually, even through their in conflict, you don't normally on everyday Earth-like scales, they don't come into conflict because one is only there for really small things and one is more on the scale of galaxies and planets moving around and things like that. So it's hard to do an experiment that shows where they come into conflict. But that is, perhaps, the biggest impact that we could have if we could, lead. I don't think, the Cal experiments in this generation are going to overthrow Einstein's theory of gravity. Though I think they will be, very interesting. They could be sort of textbook examples of, why Einstein still seems to be right. That would be, people would be very interested in. But a follow-on experiment might actually be able to see something someday.
So another aspect of Cal is that it's a technology demonstration mission. So it's the first time that we're using laser cooling in space. It's the first time that we're doing most of this in space. So the missions that will follow, this facilitates that.
You spoke of the doppelganger effect, and I was wondering if there's any relation to the red light effect
in astronomy,
to the Big Bang Theory. And, and I've heard reasonable doubt to the Big Bang Theory and the red light shift. I wonder if there's any relation between quantum physics and physics.
Sure. The physics behind the Doppler shifts that we see in astronomy is very similar to the physics that we see in Doppler shifts, in our labs. That's pretty well understood. It's why we believe those measurements coming from astronomy. One of the things that the astronomers see is that the universe seems to be accelerating, it seems to be expanding faster than they thought, and that's not well understood at all. It's a theory of dark energy. And we have actually one of those teams, the team with Holger Mueller that's doing the test of equivalence principle, dropping the potassium and rubidium atoms, and potassium atoms together. They will also do some measurements that can test one of the theories of dark energy and might be able to give some insight or more likely just kind of rule it out as a possibility. So,
Excellent presentation. Thank you.
Thank you.
Hope you didn't indulge two more questions.
We do have to, I think, cut it off by 8:30, though. So.
First one had to do on test subject selection. Why weren't noble gases with full valence shells used as opposed to?
That's a good question. Rubidium is kind of the workhorse. So at this point, we have groups around the world have Bose condensed a number of different species. I forget whether it's up to 13 or 14 or something, including some of the noble gases. Helium has been Bose condensed. Hydrogen has been Bose condensed. But the easiest one, it turns out to be rubidium, and so it's kind of the workhorse. And then potassium is chosen as the second one because its wavelength is fairly close to the rubidium one, so you can use a lot of the same optics and things like that. So,
And then partially related to that, when you get down to the picoKelvin levels, and at the dimension that you're dealing with in terms of individual atoms, you mentioned that light was used to pass through the cloud to determine its presence.
Yeah.
Isn't that a massive perturbation for it, and how do you?
Oh yes, it is a huge perturbation. In fact, it completely destroys the condensate. So I didn't really mention that, but when we make this, when we go through those steps of laser coolant, evaporative coolant, and then we make that condensate, typically we can only measure it once, and that measurement actually destroys it. There's some tricks that we can play, that we can move some of the atoms into a state that's kind of invisible to our laser beam that might let us look at it, take a couple of pictures of it. But basically those pictures are destructive and they destroy the condensate. So you need the system to be very reproducible, and you take your data by doing an experiment hundreds of times and building up statistics that way.
Thank you.
I have 2 questions also. First of all, I think you mentioned that it's something like millions or billions of times colder than anything previously constructed. And I'm wondering, since you're talking about a small fraction of a degree, how do you measure millions or billions of times colder? Is it by the movement of subatomic particles, or how are you doing that?
It's because we can look at them for a fairly long time. It's actually one of the reasons when we make these cold temperatures, one of the reasons we can, one of the advantages of microgravity is that we can wait long enough to actually see the gas expand. And they're expanding pretty slowly when times you get to 100 picoKelvin. You have to wait a fraction of a second for the cloud to get a tiny bit bigger to show that you've done it to that extent.
So it is the speed of the particles that you're measuring when you're saying millions or billions of times colder?
It's millions of times colder than space, or than we started with, I guess, billions of times colder.
Okay. Well, the other question, I did get something on my email that referred to a Bose-Einstein condensate. If you could somehow swirl it around like you would water in a glass, that because of the zero friction, it would continue forever and wouldn't slow down. Well, does this mean that if you were to do that you would have constructed a perpetual motion machine as long as you didn't take energy out of it? Could you, or would just simply observing it somehow be taking energy away from the system?
Yeah, so people have made these little quantum vortices, little kind of tornadoes, mini quantum tornadoes inside these condensates. And they've observed them, and they flow pretty much frictionless. But the difference is you can approach perfectly frictionless, but you can only get close to it. You can't get perfectly there. So it's not quite a perpetual motion machine. It would eventually have some mechanism that would dissipate
What's the piece de resistance, so to speak?
What actually stops it? I actually don't know. I mean, the clouds themselves usually have a limited lifetime. So our clouds are limited by the vacuum that they're found in. But if you could somehow get rid of those, in principle, they should,
So it is theoretically possible to have a perpetual motion machine as long as you're just observing it and not trying to take energy away?
I think it's still not. But you can perhaps get pretty close to one with a perfect system with no dissipation.
I figured there was a catch there. Thank you.
It has to.
So we'll try to answer them pretty quickly. So the first one is, how much power does the system use? So each express rack actually has the ability to give you 2,000 watts of power. We've been given permission to use up to 1,500 watts, but we'll probably use something just about under 1,000 watts.
Another question is, are the lasers used to position the atoms as well as to cool them? And they are to some extent. We actually have a couple of stages of the laser coolant. I didn't really talk about it, but we start with a source of atoms at room temperature, and we use a set of lasers that are set up in just 4 different lasers, so they come into 2 directions, and that makes a beam of atoms that actually does transport the atoms from the region where we produce them, where our source is, where the vacuum's not that great, to a region where the vacuum is really good, and then we capture them with other lasers. So to some extent, we do use the lasers to position them, but for the most part, when we're trying to position the atoms and move them around, we're using magnetic fields to push on them. You can, though, in other experiments, you do that with lasers under some cases. Yeah.
Do I understand that temperature is relative to motion? In other words, the colder it is, the slower?
Yeah, yes.
Well, if you get things real cold, you can make matter just disappear.
Well, no. It'll get slower and slower. Quantum mechanics actually doesn't let it go all the way to not moving at all. Heisenberg finally has his say and says you can't get something completely cooled down so it's not moving at all, because if you did, you would be able to know, both how fast it's moving, like 0, and exactly where it was. And you can't measure those things both at the same time, according to Heisenberg. So there's always still a little bit of motion.
Isn't there situations where matter will disappear and then all of a sudden appear?
Quantum mechanics allows that in certain circumstances, when it interacts with things like antimatter or falls into a black hole, but not under these kind of situations.
Yeah. Well, when things can get really hot, would it solidify a particle or what?
Well, that's an interesting question. The transition to a Bose-Einstein condensation is actually thermodynamically forbidden. According to the rules of thermodynamics, you shouldn't be able to, the stable state at these really cold temperatures is just a big chunk of rubidium at the bottom of your vacuum chamber. It should be a cold, solid metal. But the time scale for that to happen is very long. And it only happens when 3 atoms have to bounce in together to form molecules to trigger that process. So yeah, if eventually, if you waited long enough, yeah, you would lose atoms due to processes that make molecules, and they fall out of your trap. Yeah.
Okay, thank you.
Thanks, everyone. Sure.